Hi, everybody. Welcome back. In the second part of our discussion of stereochemistry, again, we're following McMurry's organic chemistry textbook. What we're going to talk about today is getting into molecules that have multiple stereocenters. So we left off last time with this idea that a molecule can have multiple stereocenters and that we can, using those Kahn-Ingold pre-log rules, go through and properly name each one of those stereocenters. And so we could talk about a molecule like tartaric acid that has two stereocenters. And in the example we saw before, we saw one of the molecules was drawn in the 2R, 3R configuration. And the other one was drawn in the 2S, 3S configuration. So 2R, 3R was one of them, and its enantiomer was 2S, 3S. Well, you may have left that discussion saying, well, that's great, and I understand how the first molecule that we had drawn, when it was mirrored completely, it gave us this completely mirrored molecule, or its enantiomer. Well, you may have said, well, what happens if only one of them got mirrored? What happened if I had 2R, 3S, for instance? Well, that can happen. Of course, I could draw the molecule in such a way that, one or the other of the stereocenters gets changed. And so I'm not going to write more here because it's explained better on the next slide. But what we would say is that this pair is a pair of enantiomers. They're perfectly mirrored one to the other. But either of these, compared to something like this one I drew on the right, we would say their relationship is a distereomer. So they're non-superimposable mirror images. Some of the stereocenters are mirrored, and some of them are identical to the original molecule. That's what a diastereomer is, and specifically, we'd be talking here about configurational diastereomers. We'll see cis-trans diastereomers a little bit later. This is going to be when we talk about primarily ring structures. We'll talk about these guys. Okay. So if we look at that molecule again, so here is a molecule, and it's got two stereocenters, each of which has four distinct substituents. So if we were to number this thing, from our naming perspective, we'd have the green carbon as number 1, this top black carbon is number 2, the third carbon here would be number 3, and the blue one at the bottom would be carbon 4. So we can have an orientation where we have the 2R, 3R kind of a setup. Okay, this is not tartaric acid. I should maybe say that. This is a different molecule. Tartaric acid would have had an OH group here as well. Actually, it would have had a couple changes. OH here, would have had another acid group here. Anyway, this is not tartaric acid. This is another molecule. But we can see that if we were to name these things, we could come up with a name. And I'll let you maybe work out why this is 2R, 3R, but you'd want to, again, do like we did before, rank these substituents. Okay, so nitrogen is our highest. Carbon attached 3 times to oxygen would be second. Carbon on the rest of the chain would be third. Hydrogen is a lowly number 4. You'd want to reorient this so that our lowest group is pointed away from us, okay, or use that switching trick that I mentioned. And then you would want to go ahead and do the rotation. And what we'd find out is that both carbons 2 and 3 in this drawing are in the R configuration, whereas over here, the mirror image, they're both in the S configuration. All right, it's real easy to draw mirror images. If you think about a literal mirror sitting here, you can draw the molecule, keep the bonds in the same places. But now, just like when you look in the mirror, your nose sticks towards the mirror and it sticks out of the reflection. Just draw the groups in the same places. So the NH2 is closest to the mirror, so I'm going to draw it closest to the mirror. The OH is closest to the mirror, I'm going to draw it closest to the mirror. All right, the CH3 and the CO2H are in line with the rest of it. And then the hydrogens were away here, so they're going to be away here. All right, so it's real easy if you think about this being a mirror and think about that rotation, or that reflection. However, when we compare the molecules on the left side of the screen to the molecules on the right, we can see what's happened. This top stereocenter has stayed the same when I go to molecule 3 over here, but the bottom stereocenter rotated. It mirrored, not rotated, it mirrored. And so we see that in the naming. The second stereocenter, 2, is still R, but 3 now is S. It also, the 2R3S, also could potentially have an enantiomer, okay? And that's a mirror image of itself now, perfectly mirrored. Again, imagine a mirror right here, all right? So the R at number 2 becomes an S, and the S at number 3 becomes an R. These are enantiomers of each other. Now a diastereomer would be when you take anything from this left group and compare it to anything in this right group. And we can see it in the naming where part of the name is mirrored, number 2 here, and part of the name is the same, number 3 didn't change. So we would say these two molecules are diastereomers. Okay, it would be the same if I picked this one and that one, or that one and that one. Anything from the left pair compared to anything in the right pair. The only time that this isn't true is if, when you've done this mirroring, these two are in fact the same. And that gets us back to that idea of symmetry. We don't have that in this molecule, but I'll talk about that in a couple of slides. All right, and so here's the naming. Diastereomers can differ at some stereocenters. So some are identical, some have mirrored. Enantiomers must be mirrored, must have the opposite stereochemistry at all stereocenters. There's one more word that you'll see as we go forward, and well, we'll get to that in just a second here. So if we start with 2R, 3R, we could draw one enantiomer. Again, both of these stereocenters have mirrored. But from that starting point, we could also draw two diastereomers. Okay, one or the other has mirrored. And that's true if I started with some other stereoisomer. Okay, there's only one perfect mirror. There's more than one diastereomer. Okay, so keep that in mind as you go through. There's only one enantiomer for any given molecule, no matter how many stereoisomers it has. And so even a molecule like this, all right, this has a bunch of stereoisomers. I've got one here, and here, and here, and there, and there, and there, and there, and there. Okay, lots of them. Oh, and there. All right, lots of them. Now, the difference here between these two, if we compare their structures, is literally only this one. So these are diastereomers of each other. That's fine, because some of the centers stay the same, most of them, and some of them change, in this case only one. So they are diastereomers, but they are a special class of diastereomers called epimers. This is where only one stereocenter is mirrored. Okay, very, very similar molecules, a little bit different structure here. And if you go back and think about from chapter 4, what we talked about with bridgehead stereochemistry, the geometry here, even though this is just one little bond that's different, the geometry of the molecule in this area would be significantly different compared to this molecule. So check out the end of chapter 4 if you want a refresher on that. All right, so let's get back to tartaric acid. Now, this is where we left off in the first lecture, and here's this molecule, and we can, of course, mirror it. Looks like this. And then we can have one where we've kept part of the molecule the same as we started with on the far left, and we've mirrored part of it, and then its reflection. Okay, so technically we have 4 molecules drawn here. The thing I want you to be wary of when we look at these molecules is that, in fact, this molecule, or this one, these ones on the right, have an internal plane of symmetry. Okay? If I look at this top carbon and this bottom carbon, carbon 2 and carbon 3, are symmetrical with respect to each other. It has an OH on a wedge to the right. It has a hydrogen on a wedge to the left. It has an acid group on a dash to the top and bottom. They're symmetrical. And the same is true over here. All right, and furthermore, what I want you to try to picture is that if I were to pick up this structure, this one that I said is the mirror image, this far right structure, if I were to pick it up off the page and just rotate it around 180 degrees, okay? So that what was carbon 4 is now going to be carbon 1 up here, and what was carbon 1 will be carbon 4. If you do that, I think you'll see that these hydrogens that were coming towards me on the right, when they rotate around, they will be coming towards me on the left, just like this. And the OHs that were coming towards me on the left, when I rotate it over on its head, those OHs will be over here. In fact, these two that I generated by supposedly mirroring this molecule are in fact actually the same molecule. When that happens, and the clue where you want to start thinking about it is when you see this internal line of symmetry between the two stereocenters. Okay, when this happens, this is actually one form of the molecule, and this is what we call a meso form. Okay, so we do have a pair of enantiomers, and I jumped the punchline, one other form. So tartaric acid only comes in three forms. It's the 2R3R and the 2S3S, and those are a pair of enantiomers, perfect mirror images, and one more. Okay, because it's symmetrical, I could use either name here, but one more, so three forms altogether. All right, so I'm going to add just a little separator right here. Okay, on the left side we have the mirror image versions, the two enantiomers. It turns out if we put those in a polarimeter, I find out that the 2R3R version is our plus rotation, and our 2S3S is our minus rotation. Again, I can only tell that from a polarimeter, from a wet lab experiment. When I look at those, of course, like we mentioned, enantiomers have identical physical properties. They have the same melting point, they have the same density, they have the same solubility in water, they have the same every other physical property. The only difference between them is the direction of their rotation. Right? Same degree number, 12 in this case, but one is plus, one is minus. The meso compound, that other one that when I try to make its mirror image, it's actually identical, that one is different. So notice down here at the bottom, it has a different melting point. It has a different density, it has a different solubility, and it does not rotate light. Meso compounds are not optically active. Okay? Not optically active. So that's something to keep in mind when you're looking at structures. Many of the questions you'll see relating to these structures will say things like, which of the following are optically active? And you'd want to look at those and look in particular for that meso compound. Again, what we were looking for as a clue is right here. We see this symmetry. Okay, the bonds are the same, the atoms are in the same positions. That is our clue that this thing is a meso conformation. Or mesoisomer, I guess is a better way to say it. All right, mesos take time, they take practice. Identifying this stuff is a challenge, it's a skill set. So what I suggest you do when you're going through these is to take a molecule, draw its mirror image. Okay, that's maybe the hardest part, and like I said, if you imagine that nose analogy I made before, whatever's close to the mirror here is still going to be close to the mirror. Keep the bond symbols the same. Okay, here wedge, wedge, dash, wedge, wedge, dash. Once you do that, that's an enantiomer. Okay, so once you take the time to name one of them, you don't have to take all the time to name the other one. You know it's the opposite. Okay, so take your time with one. Drawing the other one is fairly straightforward. Naming it is really, really easy once you have that first one correct. And then when you're trying to come up with the two other ones, the other pair of enantiomers, what you'll do is you'll just keep part of it the same, right? And take the mirror from your second one and plunk it on there. And there's what should be a diastereomer of either of these two. And then you can mirror it. Okay, or just take the other pieces here and make a new molecule out of that. Okay, take this guy over there and take this guy way over there. All right, it's easy to build these 4, and once you have the name for one of them, then the names for the other ones are really, really straightforward. Most compounds will have 4, if they have 2 stereocenters, they'll have 4 enantiomers, okay? The rule here is going to say the number of total enantiomers is 2 to the n. Sorry, not total enantiomers. There's always only one enantiomer. The number of total stereoisomers is going to be 2 to the n, where n is the number of stereocenters. All right, so for these ones, 2 to the 2 stereocenters, there's a possibility of 4 total. In this particular case, because these two are identical, it's not 4, it's really 3. A pair of enantiomers over here and a meso compound. The other language we have to talk about here is racemic mixture. Racemic mixture I mentioned in the other video, but it is an equal mixture of the 2 enantiomers. So Pasteur's tartaric acid crystals were this. They can be separated into their individual enantiomers. In Pasteur's case, he got a little lucky. He could see the difference, and so he used tweezers and a visual inspection. You might imagine something like this. And again, the language here, the naming says a racemic mixture, or what's sometimes called a racemate, is an equal mixture of 2 enantiomers. So it could be written in a biological context like this, D, L, or plus minus, to show that both of them are in there. Okay. Lots and lots of pharmaceuticals have been produced with non-stereospecific chemistry. And so you'll find a lot of these out there. As chemical methods, synthesis methods have improved and we've gotten better at doing stereospecific chemistry, the FDA is giving companies patent protection, giving them the ability to rebrand something if they can make it specifically the one that they want. So in the body, it turns out that many molecules, many things that have the stereoisomer capability, one of those might be, for instance, the active ingredient in a pharmaceutical. It might have a biological effect where its mirror image does not. And so you'll end up in a position sometimes where drug companies have said, okay, look, well, one of these works and one doesn't. A classic example is the allergy drug Zyrtec. If anybody takes Zyrtec, it is actually a mixture of 2 stereoisomers, one that works as an anti-allergy medication and one that does nothing in the body. And so you take 10 milligrams of that stuff when you take a pill, with the idea that we know 5 milligrams of it is active, half of it, because it's a racemic mixture. When the technology got better, and so this is Zyrtec, and I'm not slamming on Zyrtec, this was just state of the art when it was made. Now there's another chemical on the market called Xyzal, and Xyzal you take a 5 milligram version. And the reason for that is that Zyrtec is you're taking 10 milligrams of the mixed racemate, 5 milligrams of it is active. In the terms of Xyzal, you only take 5 milligrams because it is only the active ingredient. It's only the one stereoisomer. So the FDA is encouraging this better chemistry, developing new methods, using new technologies by giving brand protection for a new product. So lots and lots of examples out there. In most cases, what we found is that one stereoisomer works and one stereoisomer does nothing. There are some cases in history, thalidomide is one, where the one stereoisomer causes damage, actually. And you could look up thalidomide if you wanted to. There's a feature on it in our textbook as well. In that particular case, we found that our body actually can interconvert the two. And so there is no safe way to take thalidomide if you are, particularly in the case of pregnancy, which is where it was a problem in the first place. So the method, how we do that, we can't, of course, separate enantiomers by physical properties because they're all exactly the same. We don't have a practical way to separate them based on light rotation. So what we do instead is we react them with something. and something that is itself chiral. And so here's an example of an acid-base reaction. So here's lactic acid. Of course, it's an acid right there. And here is methylamine. This nitrogen is basic. If we do this reaction, we could get a racemic salt. All right, so this would be called like methylammonium lactate. And we'd have the R version and we'd have the S version. Okay, so it's still a racemic mixture. These two salts would have identical physical properties because they are themselves enantiomeric, right? It doesn't help us. We can't separate them. However, what if our base wasn't achiral? What if our base was chiral? All right, like here. If we were to use this one, we have the same nitrogen, the same electrons, the same basicity, so we can do the same reaction to form an acid-base salt. However, since we were using a particular enantiomer here, a particular molecule, a stereoisomer of the base, now what we've done is the lactic acid part is still enantiomeric, but this part's the same. So these now are diastereomers, and diastereomers have different properties from one another. So diastereomers can be separated. And so in this case, what we could do is we could separate this top one from this bottom one and either just put the active ingredient right into a pill and say we have a salt. Okay, fine. Plenty of our pills that we take are salts. Or we could undo this acid-base chemistry to then just get the lactic acid isomer back and put that into a pill. Of course, we're not taking lactic acid, but you get the idea. If this was some pharmaceutical that had stereochemistry, we can use this diastereomeric kind of a reaction, not just this one, but any reaction that would make a diastereomer, preferably one that we could undo later on. All right. The last big topic in the chapter is this idea of sort of predicting chirality of a reaction. And this gets us a little bit into using the hybridization that we picked up earlier on in the semester. So thinking about hybridization in a practical way. So here's an example. What's the stereochemistry of the product? I should say all these examples with page numbers, the pages might vary depending on which edition of the book you're looking at. All right, that said, the question here is, does the product have the same stereocenter or a different stereocenter than when I started? All right, so let's just look at this example. This is forming an ester. So the reaction of an alcohol with an acid, a little bit of catalyst will generate an ester. We'll talk about this reaction all over the place later on in the course. But the big question here is, does the stereocenter change? Well, where is the stereocenter in lactic acid? It's back here, right? It's that carbon that has 4 different substituents attached. That carbon is here. It did not participate in the reaction. So if I had started with R lactic acid, I would have ended with R methyl lactate. If I started with the S form, I would have gotten the S form. If I started with both racemic mixture, I would have gotten both. All right, and that's kind of shown here. The naming on an ester, we haven't really covered that yet, but you'd put the S or the R before the part that is actually S or R, so methyl R or methyl S lactate. If I started with a racemic mixture, guess what? I'm going to get a racemic mixture of the ester products. The stereocenter was not involved in the chemistry. The chemistry was happening out at the acid group. Another example, we could think about this kind of a setup, and I sort of already showed you this when we were talking about this in the first place, but what stereoisomers would result? Well, the plus and minus, this remember means a racemic mixture, so I've got R lactic acid and I've got S lactic acid, and they're mixed together. I'm going to react them with an S compound, and so what am I going to get? Well, I'll get an RS and I'll get an SS. Okay, what's the relationship between these? Well, part of the molecule is identical, part of the molecule has mirrored, and so these are diastereomers. Finally, what if a molecule doesn't have chirality, but we're going to do a reaction on it? We can think about this. If we talk about a molecule that is not itself chiral, but if we do a reaction at that spot, we can make it chiral. This example is showing a ketone, which of course is sp2 hybridized. It doesn't have 4 groups attached, and so it's not chiral, can't be chiral. But if we were to hydrogenate it, for instance, we'd add a pair of hydrogens here, one to the oxygen, one to the carbon. And so now this carbon in pink is chiral. So the logic here says we want to be able to identify or distinguish between the 2 different faces of this molecule. Remember, sp2 hybridized carbons are flat, right? We call it a trigonal planar structure. So they're flat. So if I were to imagine this molecule from the side, it would be flat. That hydrogen molecule will either attack from this side, or it would attack from this side to add on to that double bond, okay? And so if it attacks from one side, I'll get one kind of stereochemistry. If it happened to attack from the other side, I'd get the other kind of stereochemistry. That would be a mirror image kind of a scenario. And so I would like to know maybe a way to identify one side or the other, one face of this sp2 hybridized carbon or the other. And so the way we'll do that is that we will think about this molecule flat. Okay, so imagine it laying flat on this, slide or whatever, this piece of blue stuff. We're going to use the same con-angled pre-log rules to number our 3 substituents here. So oxygen has the highest atomic number. Second, we run into a carbon down here, but the carbon on the right then connects to another carbon. So this carbon beats out that hydrogen. So 1, 2, 3. If I were looking down on this structure, I would see that as a rightward rotation. In real stereochemistry, we would have said that's an R, but to distinguish this as prochirality, we're going to say it's RE. All right. The word that led to R in the first place was the word rectus. So we used R before, now we're using RE, the first 2 letters. Okay. If we were to imagine looking at this from underneath, and draw this out if you want to and hold your paper up to a light or something to look through it from underneath, we would have ended up seeing the opposite. It would have looked like a leftward rotation or counterclockwise rotation. So instead of S, that was for sinister before, we'll say SI. So the RE face is this one. The SI face is that one. All right. And so here's the picture. When we add the H from the top, we'd push those other guys downward like this. If we added the H from the bottom, we'd end up pushing these upward a little bit. And what I want you to look at here is that adding to the RE face didn't necessarily give us the R isomer. Okay, just like plus minus and RS aren't necessarily related, the prochiral face designation and the end product designation is not necessarily going to be the same. It depends on what reaction we're doing. All right, in this case, we're adding a hydrogen. That's the lowest ranking group. And so that gives us this result. If we were doing some other reaction that added something different, our rankings on this product molecule would be maybe different. And so the S or the R might be different. So bottom line here, a question might say, what product is formed if hydrogen is added to the RE face of 2-butanone? Okay, we'd say, okay, hydrogen's adding here. It's going to look like this. And now I'm going to name this guy all by itself. Forget the RE stuff from the reactant side. I'm going to rank and name these guys just like I know how to do. Okay. So here's prochirality at an sp3 hybridized atom now. All right. If we were doing a substitution, so here's a case where I might be substituting a hydrogen for something else. All right. The starting material was not chiral because it had 2 hydrogens on that prochiral center. Once I replace one of them, of course, now I do in this molecule have 4 different groups. This is chiral. All All right, and so we're going to use, again, some language. I need to be able to differentiate between that hydrogen and that hydrogen, because if I replace this top one, that'll give me one product. If I replaced this bottom one, it would give me the other product, a mirror image. And so the language here is going to use the prefix pro. In this case, what we'll do is we'll say, let's replace it. Let's go ahead and do that substitution. Here we're using deuterium, okay? It could have been anything. They're using deuterium so that we can rank them, but we could have replaced it with chlorine or something else, whatever. In this case, if we replaced the green hydrogen on the left with this higher ranking thing, our rankings would say 1, 2, 3, 4, and thankfully for us, the blue hydrogen, the fourth group, is pointed away already. And so we see that R-word rotation going clockwise. So replacing that green hydrogen with something else gave us the R configuration. So we would call that green thing pro-R. So it's the hydrogen that when it's replaced or before forming the R configuration. The blue one would be labeled pro-S. Again, if we already know one, we can know the other for sure, but the way to rationalize it is to look at this. Again, our rankings are the same. 3, 4, okay, and it looks like 1, 2, 3, it looks like we're going rightward again. However, notice that our lowest ranking group is facing towards us. We would need to swap these guys to get it in the right place, or turn the molecule around to get it in the right place. And this is our S isomer when we do that. Okay. So that one would be called pro-S because replacing it gives us the S isomer. So when we talk about sp2 hybridization, we're going to say Re and Si for the two faces, and then we're going to name the products based on the way we've learned to name them already. If we're talking about sp3 hybridized prochiral centers, we're going to use pro, pro-R, or pro-S. Right now, prochirality, I mentioned a couple times throughout these two videos that chirality is really, really important in biological systems. Sometimes less so in the lab, but more so in biology where shape rules function. And so here's an example. In the citric acid cycle, when we look at this cycle, right? So it's a series of chemical reactions and metabolism of sugars and other things that typically represented as a cycle. Got about 8 steps or so in typical drawings. But when we go from fumarate, which is shown here, to malate, the isomer that's formed of malate is specifically the S form. Why don't we get both stereoisomers here? If I do this reaction, if I add water across this double bond in a test tube, the OH from the water will add equally to the Re face and to the Si face because this is a small planar molecule. It's tumbling all over the place in the test tube. And so there's sort of an equal likelihood that the water in a test tube would be able to attack either face. And so if I did this in the lab, I'm going to get a racemic mixture of malate. I'm going to get both. In the body, we don't. We only get the S form. Well, why? That's because this isn't being done by naked molecules floating around in a test tube. In the body, we typically have an enzyme, a protein-based material that's going to form an active site where the chemistry can happen with certain pieces of that enzyme. And so as our materials diffuse in here, they're going to sit in there in a certain way so that they can interact with the enzyme properly. And so one face gets presented preferentially to the other one. It's not stochastic like we would get in a tube. And when we look at the enzyme that does this, the fumarase enzyme, its crystal structure is known. If you like crystal structure stuff, this is the protein database code for it, 1YFM. You can look that up. But the active site in fumarase is really deeply buried down in here. You can see the little molecules can fit down in here. And so what ends up happening is that that flat molecule ends up sitting in there in a particular orientation such that part of it and not the other part is accessible to the enzyme to do its work. And so we get one isomer, which is pretty cool. Because of the structure of this large fumarase enzyme, it holds the reactants in the right place, so we get a specific stereoisomer being produced. It's the same logic for why one stereoisomer might work in the body and the other one doesn't. Like in the allergy example I gave, one of those forms can fit properly into a receptor, for instance, or some other protein structure where the other one doesn't fit properly. And so it's a matter of three-dimensional shape, or as we say sometimes, function follows form. All right, here's another example, alcohol dehydrogenase. This is the reaction that's going to convert ethanol and other small alcohols into aldehydes. So ethanol to acetaldehyde, for instance. This is the first step in detoxifying ethanol if it were ingested. So here's ethanol. It is an achiral molecule, right? It has two hydrogens, but it has prochirality. And so these are labeled as the pro-R and the pro-S hydrogens. The thing that's going to do the actual chemical work here, that's going to do the oxidation of that alcohol to an aldehyde, is the cofactor NAD. We see NAD and FAD and other cofactors throughout biochemistry, but what this thing is doing, if we sort of pay attention to the chemistry that's going on, is that this site is going to be reduced. So it already had one hydrogen attached. It's going to take another one as it oxidizes this OH group to an O, to an aldehyde, to a double bond oxygen. And so when we look here, we can see what's going on. That specifically this pro-R hydrogen is being removed. All right, and how does it get that specificity? Well, it gets the specificity again because there's an enzyme involved. The enzyme is called alcohol dehydrogenase, as I mentioned up at the top. If I did this kind of reaction in the lab, again, I would get an equal chance of either of these H's being removed. But in the body, we have an enzyme structure. So this is a different way of looking at a protein structure. The gray bits are all of the protein structure, again, from the protein data bank. This was one of their molecules of the month. So you can look up the structure on your own, or you can follow that link. But here's the NAD. In this case, they used an analog of NAD, but here's the nicotinamide factor. There's that ring we were talking about that you saw on the previous slide. And the ethanol positions itself right here. And so we can see that there's specific contact between this face of the NAD ring and this face of the ethanol, not this face over here. It's upside down. And so we get this very specific reaction between those two parts of that molecule. And so while in the lab, chirality is a little bit of an maybe esoteric concept, we typically don't have ways in the lab, at least at the undergraduate level, we don't typically have ways of doing stereospecific chemistry, but we can do it in industry, like I mentioned. And it's really important when we talk about these fit-based or shape-based interactions. So here's a simple example. Okay, this one's showing the way that this particular stereoisomer on the left might fit into your hand. Let's pretend that the hand has to bond to this red circle, the sphere, and the thumb is going to grab this green sphere. Okay, so in the case of a protein, there's some interaction over here on the left that bonds to this group, and then that positions the red thing in the right place. If we had a stereoisomer of this, and here's one where the red and blue bits are switched, so this is the mirror image, the enantiomer, we can see that even though the green and the gray bits line up, the blue bit doesn't fit where it's supposed to. So this could be two different mirror image pharmaceuticals, like the two components in Zyrtec. One binds to your histamine receptor and the other one doesn't. It could be the case of, like we just saw with those two enzymes, a cofactor or otherwise some molecule sitting into an enzyme active site. And this is really, really important. We see another example in terms of scent. These are two molecules, and I sort of wish that in this picture this was drawn flipped over. But if you flipped it over, you'd see that the difference is just the stereochemistry at this one carbon. All right, they're giving us the sort of experimental designation here. This one's a positive light rotation, that one's a negative. If you wanted to, you could go through and name these stereocenters with S and R designations. But the point here is that these are identical molecules except for that stereochemistry. The one on the left is where the thing gets its name. This is in a lot of citrus fruits, but in particular lemons and limes. So it's called limonene. The mirror image of that is found in pine trees. So oftentimes we think about pine, the scent of pine as having that same sort of clean or refreshing scent as a citrus fruit. So you'll see, a lot of cleaning products like Pine Sol, okay, has the name pine in it, but it kind of smells a little citrusy. But these are mirror image molecules that have a different scent. Again, because scent is dependent on receptors in your nose and mouth binding to specific molecules. So if those molecules are shaped differently, they interact with different receptors. I should say here the field of scent and taste chemistry is incredibly complex. There are huge companies and research labs at universities that are doing just mountains of work trying to understand how scent and taste contribute, how molecules either impact the direct way that we taste or smell something, or impact the way that we don't taste or smell other pieces of that complex product when we talk about food or drink. It's really, really interesting stuff. So if you're interested in that, there's plenty of labs you could check out, or you can certainly send me an email. I'll give you some leads. Lastly, just as a real quick wrap up, I did mention a couple times that hydrogen isn't always our lowest rank. Of course, if a stereocenter doesn't have a hydrogen, that's fine. You would just rank whatever's attached, the 4 groups. But if we didn't have 4 groups in the first place, and that can happen with heteroatoms. So here's a nitrogen, here's a phosphorus, here's a sulfur. All of them have a lone pair of electrons. We can still consider these chiral. The lone pair of electrons would just be counted as an atomic number of 0. So that's our number 4 ranked substituent, lower even than hydrogen. Okay, and then so that's a 1, sorry, and the rest of our rankings are the same as we learned based on atomic number. Same thing here. I would say that's my lowest rank. My short carbon chain is going to end up being number 3. My longer aliphatic chain is number 2. My aromatic ring is number 1. I'd rank it the same way. I'm going to run into a carbon in all 3 cases here, and then it's a matter of what those carbons are attached to next. Similarly over here, this is methionine attached to an adenosine. So in biology, we call this SAM, or S-adenosyl methionine. Notice that the sulfur without this group attached would not have been chiral. It would have had a lone pair of electrons right here as well. But once it's bound, now we have 4 different things connected. We have a lone pair that is lowest on the totem pole, and then we have our 3 carbon groups we'd have to go out and rank. Again, tied at step number 1, and we go out from there. So I give you the answer here. You can prove to yourself that it is the S stereocenter. All right, and so by way of wrap up, there's a ton of material in this chapter, and depending on how visual your mind is, you may need to take a lot of time to practice with those model kits. Okay, it's really valuable time that you can put in right now. So we talked in the beginning about chiral molecules and chiral centers and the concept of handedness, mirror imaging, enantiomers that are perfect mirror images of each other. We use that R and S notation at each stereocenter versus optical rotation that's experimentally determined with plus or minus based on the overall light rotation of the molecule. We talked about how we can name stereochemical stereoisomers based on their names, how we can draw structures from names and calculate names from structures. When we have multiple stereocenters, then we got into the idea of distereomers, where part of the molecule is mirrored and part of the molecule is conserved. And the instance where a pair of apparent enantiomers might actually be just one compound if there's internal symmetry, so-called meso compound. The idea of racemic mixtures as a perfect balance of the two. This often happens when we use non-specific chemistry to generate those molecules. We talked about how we can resolve those based on using a reaction with another chiral molecule. So we can get two different distereomers and separate the two. We can predict chirality based on the physical shape of something. We talked about nomenclature here of how we would use the RE and SI nomenclature for sp2 centers, or the pro-R and pro-S nomenclature for sp3 centers. So chapter 5 gives us a lot to work with. Take your time, practice, do the problems in the text as well as looking at the problems at the end of the chapter. On our online learning system, I've got some additional worksheets and practice links and stuff for you to play with. But have that model kit handy for right now. Use it, practice, get comfortable drawing molecules and trying to rotate them in your head, rotate them on paper, and then rotate them in 3 dimensions on your model using either your model kit or the MolView modeling software to do that. Okay. With that, I'll say thanks for listening, and of course, email me with any questions. And otherwise, have a great day. Take care.